Good morning. This is Ms. Billerbeck, and we're going to talk about section 5.2, piecewise defined functions. A piecewise defined function has different rules for different intervals of its domain. So remember, domain has to do with the x. Range has to do with the y. So if I have x greater than or equal to 0, then this would be 2x. A positive 2x, so I'd have a positive slope here of 2x. Now, when x is less than or equal to 0, it could be equal to negative 2x. Now, this is interesting that x is 0 actually works for both of these, and that's kind of rare that we have an overlapping domain right there. But it only works because 0 times anything is 0. So that's why we can overlap right there in this specific case. So this function here on this side would be your negative 2x, so it would have a negative slope. So it's just a reflection about the y-axis. And if we wanted to write this as a function, we'd write it like this, where it becomes 2 absolute value of x. So that's what we're doing. We're breaking up the absolute value into 2 different sections. All right, so this section, we want to express f of x equals negative 3 times the absolute value of x as a piecewise defined function. So a good thing to do is to actually put in a few values of x and y to get a good feel about what is happening in this range here. So if I have x here and y here, so let's put in a few values. We know that it'll probably be around the 0 value, so we want balanced values around that 0. So if we put in 0 here, -1, -2, that should give us a good idea about our output. So we're going to input those values. So the absolute value of -2 is 2. -3 times +2 is -6. Then we put the absolute value of -1. We have 1. So -3 times 1 is -3. 0 is just going to be 0. The absolute value of 1 is 1. So -3 times 1 is -3. And we can see that this is just going to be a reflection here. So let's plot those values now. So we have 0, 0, and -1, and we're going to go to -3, and -2, -6. So it's a pretty steep slope. And then we have negative, at 1, we're down to -3, and 2, -6. So we see we have a nice V pattern going on. So let's go ahead and graph that once I find a straight edge. All right, so we have to be resourceful sometimes, so even a pen is a good straight edge. So there you go. Once you get the handle of how to use your pen as a straight edge. Okay, so we see a nice V shape going on there. And we see that we have an increasing slope between x, or as x is less than 0, we have an increasing slope. So let's look at that slope. So we have a rise here from 6 to 3. So that's a rise of 3 and a run of 1. So if we were to break this out as f of x as a piecewise function, we would write it like this. And that's supposed to be a nice little tilde right there. All right, so this function here, we have a slope of 3. The y-intercept's at 0. So we'd write 3x for x is less than or equal to 0. And then this one, we have a rise of -3. I guess I could go on the other side for that to show you the negative. So we have a rise of -3 and a run of 1 right here. So for -3x, that would occur when x is greater than or equal to 0. Again, this is an unusual situation where we would have overlapping values at 0, where it could be 0 for either function. So that's very unusual, okay? So don't assume that's going to happen each time. All right. So let's take a look at this. First, let's graph it, and then we're going to try to figure out what exactly is happening. So this one, we have two different functions. So when we set up our tables, we're going to have to be looking at these functions, y equals x minus 2 for a graph, and y equals -2x plus 3 for a graph. Okay, so when we graph something, we're going to start with the y-intercept. So let's start with -2. And we have a slope of 1 right here. So we're going to rise 1, run 1. Rise 1, run 1. So we see we have a nice little slope there. Here's another straight edge that's a little better. So we can draw this. Now we have to look at where this is happening. Okay, so we can plot this. See how I started with the y-intercept, and I'm just going to keep rising and running. But the thing is, we have a restraint here on our domain. X has to be less than or equal to 1. Well, 1 is right here. So that means it can be equal to 1, but it has to be less than 1. So this function is going to be right here, going down this way, and it won't be going up on these points here. Okay, so that's important to understand. Where is the domain restricted? Okay, so it's restricted x is less than or equal to 1. This one, x is greater than 1. So we don't see an equal point, an equal bar here. So we actually have to have an open point. So let's start by getting an idea of where is this line, and then we're going to look at this domain to see how it's restrained. Okay, so we start at the y-intercept's 3, so we're going to put a point here at 3. We're going to rise -2, run 1. Okay, we see that we're greater than 1, so we're going to have to rise -2, run 1 here. Okay, so here at 1, we're going to have an open point. Okay, and we rise -2, run 1. Okay, so this point, even though it helped us understand where is this line, we don't have that in the domain. X is 0 is not there. We can't put it in the graph. So when we draw this piecewise defined function, we're going to have something that looks like this. So we see right here, if we were looking at the vertical line test like this, we see, oh, hey, they're overlapping, but hey, they really aren't. Look, one's a solid point and one is an open point. They are not overlapping. This one's not including 1. There's no equal bar there. Okay, so it is still a function, but it's a piecewise function. It is not a continuous function because it has a break in it. All right, so you're probably wondering, why do I need to learn piecewise functions? Well, your parents, if they are paying water bills, okay, and energy bills, you know, we pay SMUD bills in Sacramento. So they have different tiers for different users, believe it or not. So if you don't use a lot, they don't charge you a lot. They even will pay you back some if you have solar panels and you're giving back to the system. Okay, so but if you're a big user, then they're going to charge you a little more per gallon of water used. Okay, but if you are an exorbitant user, if you use way too much water, they think you're super rich and they think you have lots of money, okay? Which is typically you've got a big estate. And if you haven't changed your zoning to orchards, you're going to pay a lot of money for that water bill to water all your landscaping or your pool or something. So they're going to charge you a great deal of money every month for that excessive water use. So this is an idea of how piecewise defined functions are used in our real life. So conservation, does water conservation actually save money? Well, it does. It saves you money. This is the water conservation person. So larger estates typically pay more for water because they have more landscaping. They have a pool. There's a lot of evaporation, so they have to keep refilling the pool. So there's a lot of water use at big estates. So they get put into a bigger tier. So if you can afford a bigger estate, they feel you can afford a bigger water bill. So that's one way they get a little bit more money. And they make it a little easier on the people who don't have a lot of money to keep their houses. All right, so this example came from your book, and I actually don't do these examples normally, but I thought this was really an interesting example. So this is something you might do for field trips, or say you were having a rally at a really big high school and you had to separate different people, so you had different wristbands for different times to go to a rally. Then you could order wristbands in bulk and save money. So if you ordered 0 to 50 wristbands, then it would cost $2, and then they get you with some shipping of $20 for that. So if you order 51 to 100 wristbands, then the wristbands cost $1 each, and the shipping's $10. However, if you order more than 100, the cost of the wristband is 50 cents, and there's no shipping. I'm sure you've seen things like this if you're doing any kind of fundraising when you're buying things in bulk. So these are piecewise defined functions. So let's represent this. So if I have 0 to 50, so if I write f of x here, and it's going to equal this, if I wrote these functions out, this one for 50, I'm going to write the number of wristbands, let's say x, or let's use x for the number of wristbands. I'm just going to write wrist, okay? Well, I'll abbreviate wristbands. Okay, so then we see we have a slope here, so it's $2 per wristband. So we're going to write 2x, but then we have a shipping fee, so we have to add $20 there. So it depends on if I ordered 40 wristbands, it's 2 times 40, which is 80, plus 20 is $100. Okay, so now we need to put the restriction, so that is x is 0, and it's right there. Okay, so we've got our restriction. Now for this one, we have one for our slope, but we don't write 1 in front of a variable, so we just write x. We do have shipping, so we add plus 10. And the restriction on the domain is it's 51. And it ends with 100. Why do I not worry about what's between 50 and 51? Can we order partial wristbands? No. So we're just using counting number or whole numbers here because 0 is included. So I'm not going to worry about 50.1. I can just add 51 here. Okay, the last one is 50 cents each if I order over 100. So there's no shipping, so I have no y-intercept. So I'm going to write 0.5x, and it's not adding anything. And then I'm just going to write x is greater than 100. And it's just as simple as that. All right, so if we look at, well, what if we didn't know we were going to need over 200 wristbands or 200 wristbands, and we order 100 wristbands and we run out, so we order 100 wristbands again. So how much does that really cost us? So let's put that in here. So if we order 100 wristbands, that's just 100 plus 10, so that's $110. And then we order 100 wristbands again, so that's again $110. So 2 times 110 is $220. So that's if we didn't plan well and we ordered 2 separate orders of 100 versus ordering 200 wristbands. Now if we order 200 wristbands, it's half of 200. So if we order 200 wristbands, that's 0.5 times 200, which is $100. So see how planning would really help save $120. That's very significant. And the manufacturer will not say, oh, sorry, we're going to give you the $200 cost, or, oh, you ordered 100, now you want 100 back. I think that we're not going to charge you. They wouldn't say that. They'd charge you $110 again. Even that. So if you had ordered the $200 wristbands at first for less than ordering 100 wristbands, then you should have done the math first to see that, oh, it doesn't matter. I should order 200 wristbands. It's much cheaper than ordering 100 wristbands. Isn't that crazy? But that's what piecewise-defined functions do. They have different tiers for costs, and it's a very important thing to explore your options by using your great math skills. So that's it for section 5.2, and I hope you have a wonderful day. Bye-bye.